Well, thank you very much for the, wait a minute. Thank you very much for the opportunity to speak here. So the title of my talk is Quantum Cohomology of Symplectic Resolutions and Moduli Spaces of Gaudin Algebras, some slight modification. So I think I'm the only, I spoke at this previous iteration of this summer school 4 years ago in Paris, and I seem to be the only one of the speakers who was there 4 years ago, so maybe I didn't do a very good job, so now I'm supposed to make amends by trying harder the second time. So I tried to set it up so this lecture series is like a little complementary to what I did 4 years ago. And if you're interested rather in what I just said 4 years ago, well, I wrote up lecture notes of that, which you can find in the archive, and there's some nice pictures in those lecture notes, so if you're bored, you can always look at the pictures of those lecture notes. So there I mostly focused on symplectic duality. And symplectic duality will play a small role. I mean, maybe more than a small role. It will play some role in this lecture series, but not be the main focus. OK, so what's the goal in this lecture series? So we're going to be interested in, these guys, conical symplectic resolutions. So I'll start with the, don't worry, I'll explain what that is shortly. So, but this is just the overview. So we'll start with the conical symplectic resolution. And there's something called a quantum multiplication on its cohomology. It turns out this quantum multiplication depends on a parameter called the quantum parameter, which lives here in some open subset of H2 of y with coefficients in C star. So our goal in this lecture series will be to adjust the following two questions. So the first question is, for specific examples of these y's, especially, well, only, I suppose, for ADE quiver varieties and for affine Grassmannian slices. Those happen to be symplectic dual. For those specific y's, we will describe this quantum multiplication by means of some geometric representation theory. OK, so that's the first goal. Generally speaking, this stuff I'm describing in part 1 is not my own work, and it goes back maybe 10 years, some of it early, some of it less, some of it more, due to Okunkov and collaborators. In the second part of my lecture series, then I'm going to segue into some more recent work that I've been doing with Leonid Rybnikov, who happens to arrive here in a couple of days, about studying compactified parameter spaces for these algebras. So this parameter here lives in this open subset here of a torus, and we're going to be interested in compactifying that open subset. I'll explain what that means and how we do it when the time comes. So, OK, here's the plan, which is maybe not so different from what I just said. We're going to discuss generalities on symplectic resolutions in quantum cohomology. And then we'll discuss quantum multiplications for quiver varieties and affine Grassmannian slices. And then we'll talk about these compactified parameter spaces. And well, there's 3 things, and there's 5 lectures. And I don't really know how the 3 will distribute over the 5, but I guess roughly 1.5 each. We'll see how it goes. OK, any questions? Great. OK, so let me begin with the definitions. OK. So what's a symplectic resolution? So that'll be the basic building block for all of what I do. So let's be clear on it. So we have a pair of varieties over the complex numbers, x and y, and a morphism between them. And all 3 objects have to satisfy some conditions. So y should be smooth and symplectic. And in this series, symplectic always means symplectic in the algebraic sense, or holomorphic symplectic, not real symplectic. OK, so everything is always in the category of algebraic varieties. And usually I work over the complex numbers, though it's not strictly necessary. OK, x, the image of this map is affine, normal, and Poisson. And the map pi itself is projective, birational, and Poisson. Poisson here means that it respects the symplectic structure on y compares to the Poisson structure on x. So pi is like kind of a resolution in 2 ways. On the one hand, it's a resolution of singularities in the usual sense, in the sense that the y is smooth and pi is projective and birational. So in the usual sense of algebraic geometry, it's a resolution of singularities. But it's a sort of also a resolution in a kind of symplectic sense, because x carries this Poisson structure, and a Poisson structure is kind of like a degenerate symplectic structure, and y resolves that degeneracy in the Poisson structure and turns it into a symplectic variety. So that's called symplectic resolution. A couple of more definitions related to it, and then we'll come to some examples. Okay, so we're going to consider two kinds of tori acting on this pair y and x. So the first is going to be called I'll just write it as C star. So y is called conical if we are given an action of a C star, a single C star, on the pair y and x, and I didn't write it, but pi should be C star covariant, such that the action is conical. So what that means intuitively is that the C star action contracts x to a single point. That's why it's drawn as x, because it gets all contracted to the middle here. And algebraically, what it means is if we take the coordinate ring of x is affine, so it's completely determined by its coordinate ring. And this action of C star on x gives rise to an integer grading on the coordinate ring of x. And I demand that this integer grading be actually a non-negative grading, with the 0th graded part being just the complex numbers. So this point in x comes from a natural augmentation ideal of this thing. Just project onto this copy of C at degree 0. And another thing which we demand, which I'm not going to go into too much, is that this action of C star should scale the symplectic form on y. And there's a slight difference. Some people work with weight 1 actions, some with weight 2 actions. I'm not going to be concerned with the difference. Okay, another thing we're going to look at, though, is another torus, which is going to be a Hamiltonian torus action. So we're going to have another torus, T. So two tori. One's always going to be called C star, one's always going to be called T. And this torus is going to act, again, on both x and y. Pi, again, will be equivariant for this new torus action. The new torus action will commute with the old torus action, with the original C star, so we'll have a T cross C star action. And the new torus action will be Hamiltonian. Hamiltonian means that there's a moment map for its action. And that means that there's this moment map equation relating the action in symplectic form, the moment map, and so on. It's not that important if you haven't seen it before. It does preserve the symplectic form. And maybe what's slightly important for this talk is that I'm also going to assume that there's only finitely many fixed points in y for this C star, for this torus action. Not for the C star action, but for the torus action. Okay, let's look at an example. So this is the simplest example of a symplectic resolution, the kind of prototypical example. So we take T star P1, which we picture as this hyperboloid, or a nuclear power plant, if you prefer. And it maps to this nice double cone here, collapsing the middle. So there's a P1 which gets collapsed here. So this map is birational. In fact, the fibers are all points except over this point here, where the fiber is a P1. I like to think of this in what I would say linear algebra terms. So in linear algebra terms, here I represent this cone. I think of it as the nilpotent cone of SL2, which just means a set of nilpotent 2x2 matrices. So that's a nilpotent 2x2 matrix. So it has trace 0, and it has determinant 0. So 2x2 matrix with determinant 0 and trace 0, that's a nilpotent 2x2 matrix, also known as an A2 singularity. It occurred in the last lecture as well. And I think of the cotangent bundle of P1 in this linear algebra terms as a pair of a matrix A, a line L, so living in matrices cross P1, with this property that the matrix kills the line and maps C2 inside of the line. And I mentioned just above that we were supposed to have two actions, one of C star and one of a torus. So the C star action will be this conical action. In the matrix land, it will just scale the matrix, the whole matrix, by the complex number. So it'll send everything down towards 0. So all these variables u, v, w, and so on will all have weight 1 for this action. And well, on this side, it will do the same thing. We'll leave the line alone and just scale the a. Oh, sorry, maybe I should say this. On this side, that's equivalent to saying that it scales each fiber. So if this is a cotangent bundle of P1, where you imagine the P1 sitting here. That's the contracted P1. And this C star action is the same as scaling on the fibers of that line, fibers of that line bundle. And there's another torus action. In this case, the torus happens to be rank 1, the Hamiltonian torus. Usually we think of it as C star squared mod C star. So it's the action of the diagonal 2 by 2 matrices. So the diagonal invertible 2 by 2 matrices will act by like conjugation, I guess, on the nilpotent matrices, and will act on this side by conjugation and acting on the usual way on P1. And I kind of think of this second action as being like rotating the pictures. So one action, the C star action, collapsing everything to 0, and this action is like kind of rotating. I don't know if it's a great perspective, but anyway, from that perspective, there's 2 fixed points. I didn't draw it in the picture. Maybe I'll just do it now. There's 2 fixed points for this action, namely the 0 and infinity of this P1. So it's sitting in here. There's P1, and it has a 0 and infinity, and that 0 and infinity are fixed by that Hamiltonian torus action. And I said that's one of the things we want, that there'll be finally many torus fixed points, and there are two torus fixed points. Okay. Any questions about this basic example? So you could think of this topic of conical symplectic resolutions as an attempt to generalize this example, or you'll see soon many ways of generalizing this example. Okay. So let's go on to other conical symplectic resolutions, which are generalizations of this example. So, well, the most obvious thing you could do is you could replace P1 by another projective space, or perhaps another Grassmannian. So say we take a Grassmannian, GCAN. We take its cotangent bundle, which we can think of basically in the same way. If you just ignore the fact this is 2 and this is a 1, if you write the same equations, that's a good description of this cotangent bundle. And this will be a resolution of what space? The space of matrices with rank at most k and square 0. As long as k is smaller than n over 2. If not, you should have to replace k with this. Anyway, minor technicality. And okay, so this is a nice generalization of our cotangent P1. And lots more generalizations. We could take cotangent of the full flag variety, which is a resolution of the nilpotent cone. So just all n by n nilpotent matrices. Or we could take cotangent bundle of some partial flag variety. Or we could switch to a different reductive group rather than GLN and look at cotangent G mod B or cotangent G mod P. So there's lots of options there. So this is like kind of the, I don't know, classical symplectic resolutions. And somehow now we're going to introduce some things which are not immediately of this form, but are still somehow behave very similarly. Okay, so the next class of examples, which I won't talk about in much detail, but will be the topic of Jeremy Peters' talk, are called hypertoric varieties. And much like the toric varieties we saw in the last talk, these are defined by combinatorial data. And another way of like characterizing what is a hypertoric variety is essentially the case where the dimension of y is twice the dimension of t. Well, you might be used to a toric variety has an action of a torus, and the torus has a dense orbit, so the dimension of the torus acting is the same as the dimension of the variety. And hypertoric variety is a kind of cotangent situation, so the dimension of y is actually going to be twice the dimension of the torus. You might notice that this one is a hypertoric variety, at least the torus acting is one-dimensional and the variety is two-dimensional. Okay, so I won't go into the theory of hypertoric varieties. Okay, we will see, though, the theory of quiver varieties. So quiver varieties already kind of appeared in Purek's talk. I mean, it did appear, but in a slightly different guise. So let me go over how I'm going to think about the quiver varieties. Okay, so I begin with a directed graph. And in my talks, this directed graph will usually be an ADE Dynkin diagram. Now, this is a pretty big limitation. We get kind of richer theory, and maybe I'll make a little bit comments as we go along, what happens when we go out of the Dynkin situation. But I'm doing it for a few reasons. One, because that's the situation where I really understand the quantum cohomology algebras well, and I understand this kind of compactification business that I'm going to talk about in the latter half of the lectures. So there's lots of work to be done outside of the Dynkin case, too. Okay, so usually a Dynkin diagram. Now I fix two what I call dimension vectors. So they're just a list of integers. Whoops. I guess integer is an exaggeration. A list of natural numbers. One for each node of my graph. So I is the, I didn't say it, but I is the vertex set of the graph. E is the edge set of the graph. Okay? And what I'm going to do with these two lists is I'm going to draw a picture like that. So I put the V's inside of some circles. I put the W's inside of some frames. These are called the framings. And I put arrows as drawn. So the original graph, maybe I didn't draw it. The original graph is like the A3 Dynkin diagram. And so the edges of the original graph are used to connect the V's. Okay? And V's, well, I'll go back and forth. There's like a vector space capital VI and a number little vi. And same thing with W's. Okay. Then I form a big vector space, which is the vector space of all possible representations of this quiver. So representation of the quiver with these fixed vector spaces. So representation of the quiver means I need to assign a linear map to each edge. So for each of these edges, I get a linear map here. So direct sum over all edges, hom from the tail of the edge to the head of the edge. So I put some linear map here A, I put some linear map here B, and then another set of linear maps for these vertical edges from the V's to the framings. So some vertical map, some C, D, E. Okay. So an element of N is a whole bunch of linear maps, or these vector spaces have bases, so if you like, a whole bunch of matrices. So N is a big space of matrices. And there's an action of a group G, which is simply the product of the GLs of the VIs. Of course, the GLs of the WIs act as well, but that's the whole point, is that they're like, I'm not going to consider the action of GL. WIs just VIs. That's why the WIs are in boxes. And so this product of the GL of VIs acts on N. How does it act? In the obvious way. So each one of these linear maps will get conjugated or composed or post-composed or pre-composed as appropriate by the corresponding element of G. So, so now I'm going to do something which is hard to motivate exactly, but I guess the idea of doing this goes back to Nakajima. And well, one way of saying why we do it is because everything in this symplectic resolution business has something to do with cotangent bundles. Okay, so cotangent bundle plays a big role in this thing because cotangent bundle is always symplectic. So we go to cotangent bundle. So we take the cotangent bundle of this vector space N. N is a vector space, so taking cotangent bundle just means taking the direct sum of the dual. And moreover, the dual of a Hom space, if I have Hom from V1 to V2, if I take its dual space, it's canonically Hom from V2 to V1. So N star is just the same quiver, but where I look at arrows in the opposite direction as well. Or rather, T star N is the same quiver where I look at both arrows in both directions. So it's related to in PRX talk, he did something even worse. He doubled the arrows and added all these loops at each vertex. So I don't add the loops at all the vertices, just double the arrows. Somehow has to do with like Calabi-Yau 2 versus Calabi-Yau 3, but that's not going to play a role in my story. Okay, and so I could double the edges. This thing, of course, now becomes symplectic. Cotangent bundle of any smooth variety is symplectic, particular vector space. And this T star n has an action of G, just as before. But now the action of G has a moment map phi. Usually this moment map goes to the dual, but it's not very, well, okay, it doesn't matter. The dual, you can always identify a GLN dual with GLN in the usual way. And how does this moment map phi work? Well, remember, an element of T star n is like a doubled representation of this quiver. And so given a doubled representation of the quiver, you can start at some vertex and look at all the ways of going out and back following an edge and its opposite. And so if you have, a matrix for every one of those edges and their opposites, you can compose and get maps that go out and back, and phi is just the sum of all those ways of going out and back. Actually, this also secretly appeared, I think, in PRX talk related to the potential. Okay, and then we have, related to the differential in the Ginzburg algebra. And then we're going to consider a character of this group G. So what's G again? It's the product of GLVI's. How do I make a character? Well, I just take the element of this group is just a sequence of elements of GLVI, and you just take the determinant of each one and multiply them together. So that's our character chi. And now I have the right recipe for doing this Hamiltonian reduction. So what's Hamiltonian reduction mean? Well, in this context, what it means is I take the 0 level of the moment map. Well, I could take another level, but in this talk, I'll take the 0 level of the moment map. And I take the projective GIT quotient by the action of G using this character chi. So this, well, projective GIT quotient kind of appeared in the last talk about the toric definition of toric varieties by reduction. And so here I have a projective GIT quotient. Here I just have the categorical quotient or affine GIT quotient. So this right-hand side is just spec of the G invariant functions on phi inverse 0. And the left-hand side is proj of the direct sum of the n chi semi-invariants for all n. So this produces you a variety y and a variety x and a map. What are some things that could go wrong? Usually they don't go wrong, but well, what could go wrong from the point of view? So what I want to say is that this y goes to x is always a conical symplectic resolution with Hamiltonian torus action. And most of the time that's true. So some small caveat is that this map's not always birational. And second slight problem is that the torus action doesn't always have finally many fixed points. So even when these problems arise, they're not like very big problems, so you can deal with them, but this is a good situation. And this y and x, or maybe both, are called quiver varieties, or sometimes Nakajima quiver varieties. Or Konkov sometimes just calls them Nakajima varieties. So I think this general construction I just presented is due to Nakajima. What tori do I have acting? Well, I wanted to have two kinds of torus. One, this C star. Let's start with that guy. So C star is going to be that conical scaling torus. And it's going to act on n just by scaling n. And so an element of n is just a bunch of matrices, and I just scale each one. And that action survives to this quotient. And that gives me a C star action, which will contract x to a single point. And on the other hand, I wanted that other action, that rotating action, that Hamiltonian torus action. And where does that action come from? It comes from, sorry. So remember those vector spaces W were also around, and I told you we weren't going to consider like we only were going to take GL of VI's. We weren't going to take GL of WI's. But of course, the GL of WI's does act on n, on T star n, on phi inverse 0, and therefore on y. So everything in the picture has an action of GL of each of the WI's. And now I take the what I call TW, which means like the maximal torus of those GL of WI's. So just diagonal matrices in each GL WI. And so overall, that becomes just C star to the n, where n is the sum of the WI's. And that will act on y. Okay. Let's look at some examples. So here's 3 basic examples. So it's a little hard to tell, but yeah, so let's give a number so it's easier. This 1, 2, and 3. Okay, so the first example, I take a one-dimensional vector space here. So my graph in the first case is trivial, just a single dot. So I only have one circled vertex connected to one framed vertex. The underlying Dynkin diagram is the Dynkin diagram A1, Dynkin diagram of SL2. I take, say, one-dimensional and n-dimensional. So my n is just Cn, because it's the Hom from this 1 to this n. And my G is C star because it's GL of this one-dimensional vector space. And so I end up with T star of Cn. And then I take the Hamiltonian reduction by the action of this C star. And if you've done this before, you can see that you get T star Pn minus 1. If you haven't done this example before, it's a good exercise. It's pretty elementary. You get T star of Pn minus 1. So those, for example, if you take n is 2, you get T star P1 that we started with. A slightly more interesting example is we elongate our quiver. So we take here, this looks like the Dynkin diagram of type an minus 1, Dynkin diagram of type SLN. And I just happen to choose my dimension vector v to be 1, 2, 3, and so on up to n minus 1. And then the last n minus 1 vertex, I connected to a framing where I put an n. So a priori, I could put whatever numbers I like in these circles and whatever number I like here, but I just choose it this way because the answer will be really nice. The answer is the cotangent bundle of the flag variety. And just intuitively, what's going on is that you have an action of, you have this guy. We're going to eventually double the arrows, but ignore the doubling for a second. So we have a bunch of matrices here, A, B, and so on. So each of those matrices will get acted on by conjugation by all these GLs. But at the end of the day, like the image of this n minus 1 inside of Cn will be invariant. So the image of the last one will be a well-defined quantity. The image of the composition of the last two will be an n minus 2 dimensional subspace of Cn, and so on. And that builds us our flag in Cn. And then using the arrows in the opposite direction and so on, it builds us this cotangent part. Yeah, sorry, can you? Yeah. As long as they're in ascending order, it gives you a partial cotangent bundle of a partial flag variety. Okay. And here's another example, which a lot of people like, me a little bit less so, but let me throw it in there. If you take, if you put n-dimensional, so it's like almost the opposite of this guy. So, but I have a loop. So my underlying Dynkin diagram, maybe it's worth drawing it. So here my underlying Dynkin diagram was SL2. Let me make it black. Here my underlying Dynkin diagram, this first example was just SL2. Here my underlying Dynkin diagram was SLN. Here my underlying Dynkin diagram is affine SL2, or A1 hat. So the graph looks like that. So after I frame it, it looks like that. And I put an n-dimensional vector space here and a one-dimensional vector space in the framing. And so my space n consists of the data of a linear map like so. So that's an n by n matrix. And a linear map like so. So that's an element of Cn. I mean, a map from n to 1. It's like Cn dual, whatever. Cn. And then it turns out that the resulting quiver variety you get is the Hilbert scheme of n points on C2. There's some slight subtlety in this example. Because of this loop, you have a little bit more freedom in how you do things. But ignoring the subtleties, you get roughly the Hilbert scheme of n points on C2. But this is not an ADE diagram, so it's kind of not going to be the main focus of my talk. Although, historically, this example has kind of maybe been the motivating example for a lot of this stuff, especially for a concave. Yeah?
Is there a reason for the choice of
just a natural choice. I think as long as you choose something non-degenerate, you're not going to change things. Yeah. In the second example, in the third example, I think I'll make more of a little bit more of a difference what you choose for your chi. In the AD situation, I don't think it makes very much difference. I believe in the third example, if you choose chi differently, you may get different, some different spaces. Yeah.
Another thing is, I think for the framing, there are also more ways of choosing the framing. Some people have arrows both ways, some people have it going to this side. Is there, does it matter in your case?
So I should say, like, well, first of all, certainly it doesn't matter. I mean, whether you put this guy on the side or below, of course, doesn't matter. But maybe more substantially, a good question, is that you might ask, okay, yeah, does it matter, for example, the initial orientation of my graph? And does it matter the initial orientation of all these edges that I put here? And the answer is no. If you can change the orientation of any edge in the original graph or any of the edges to and from the framing, and it won't change anything, because once you pass to this cotangent bundle, you're forgetting which way, I mean, you've got both directions. That's a slight lie, because while it's true what I just said, the cotangent bundle, of course, doesn't see which direction you put as the first one. This map is slightly sensitive to that, and but in the end of the day, the variety you get this way will not depend on how you put those, how you choose the orientations. Yeah? Yes, you do. Not on the cotangent bundle. I think the symplectic structure on the cotangent bundle doesn't depend on which way. Like, it's an affine space. It's just a vector space. So I think the symplectic structure on the cotangent bundle is not sensitive to which one is the base. Like, it's okay. Is there a way to check the time besides like okay, okay. There's no. Yeah, I mean, normally on my computer, on my iPad, there would be, but it's gone. No, it's fine. I have mine. I could put mine. Okay, great. Okay. So, I don't know. Nowadays, people say the following thing. They say that this pair of this G, so G is the group, that product of the GLs, N is that big vector space. Let me just go back. Okay. Here was G and here was N. G was the big vector space of the whole big vector space of the representations of quiver, and G is just a product of GLs, and it's acting on N. Okay? People say this pair GN is called a quiver gauge, gives a quiver gauge theory, which is an example of a 3D n equals 4 quantum field theory. So I don't know so much about what that means, but people, I mean, you can study such things more generally, but we're going to stick to this particular situation. But the reason why I'm bringing this up is because given this pair Gn, there's two constructions you can make. So now G and N could be, in principle, I mean, for my situations, it will always be that G and N that appeared just now. But in principle, this could be any reductive group. And this could just be any representation. And actually, these days, people are even generalizing it out of the linear situation. So given a group and a representation, there's two constructions one can do. The first construction is called Higgs branch construction, and that's just what we did. So you form the cotangent bundle of n, as we just did. You have a moment map phi. You take the 0 level of the moment map, and you take this projective GIT quotient. So this Hamiltonian reduction, sometimes people would write this like this, T star n. And then they put like more lines, like 3 or 4 lines, depending on how they're feeling, by G. And maybe you put like 0 comma chi, or maybe just chi, something like that. Okay. And so that thing is called the Higgs branch. So this Nakajima covariety is an example of a Higgs branch. Those hypertoric varieties that I mentioned are Higgs branches, so on. So something defined by this Hamiltonian reduction procedure is called the Higgs branch. There's another way of starting with G and N and producing or trying to produce a symplectic resolution. So even this first root, Higgs branch root, it doesn't actually usually work. If you just pick some G and N randomly, you probably won't get work, in sense, won't usually produce you a conical symplectic resolution. But it does work when you have a quiver variety, modulo the small technicalities I mentioned. Anyway, so there's another route, which is called, for trying to produce a symplectic resolution, motivated from physics. And it's called the Coulomb branch route, or the Coulomb branch. And it was introduced in mathematics, well, I guess about 10 years ago now, by Braverman, Finkelberg, and Nakajima. And so Dinakar, I think, will talk about that a little bit in the next lectures, in his talks. And these two things, the Higgs branch and the Coulomb branch, so in the best case scenarios, which is what I'm going to be talking about in this talk, in the best case scenarios, both of them are symplectic resolutions. And the relation between the two of them is called symplectic duality. So symplectic duality is like a whole package of stuff relating these two spaces, which I'm not really going to get into, but, well, you can look here if you're interested. Okay. Any questions? Yeah? Well, it's automatically of cotangent type, because I took the cotangent bundle. So usually there would be like some m, and then you change this to an m. And then cotangent type means it's cotangent of n. So it is a cotangent type automatically in my construction. Any other question?
So you had the up there, you had this example with specific G and N. Are you saying that they're normalized for any reductive group and any representation?
Well, if you have any reductive group and any representation, you can try these roots. Both roots are available to you. Sometimes you might, what you produce this way by following these roots, you might not like as much. But like, for example, this thing may typically this variety is not smooth, like even if you take the projective GIT quotient. Typically there's some orbifold singularities. So, or things could even go much worse. Yeah? Oh, there's always phi. It's a map from the cotangent. If you have it's cotangent bundle n, which is n plus n dual, and the map takes, all right. So you have G acting on n. N is a vector space. So phi goes from n plus n dual to G dual, and phi of alpha v is the linear functional whose value on a Lie algebra element x is alpha of x of v. So it has a very simple expression. For example, you could take n to be the trivial representation. From the Higgs viewpoint, it looks like a very weird thing to do. I mean, you get something very stacky, right? Because you have you get something both very derived and very stacky, because you take the 0 level of a map, which is coming from 0, so it's some kind of like derived thing to do, and then you have some stacky thing because you take this G acting in a weird way. Okay, so some kind of bad stuff will happen, and on this root is quite interesting in that case, and you get this universal centralizer stuff. I don't know if Dinakar will talk about it, but anyway, there is certainly a lot you can do, and these days people are even generalizing this thing further, and they have this relative geometric Langlands program of Bensvi, Venkatesh, and Sakalaridis. Okay. Anyway, that's not really our story. So our story in this lecture series is just going to be about these particular G and N coming from the quiver gauge theory. And I've described the first root. And now I'm going to describe the second root, but not using this BFN construction. I'm going to tell you what this Coulomb branch is, but in this case, not using the BFN construction, just telling you what the answer will be. Yes?
Do I understand correctly that there is a very concrete Lagrangian for this associated to this pair, G and N?
A concrete Lagrangian?
You say that this is quantum field theory, so there is some action. And there is
Oh, Lagrangian in that sense. Maybe there is, but I don't know what it is. Yeah, there is, but not maybe not part of this lecture series. Okay. Okay, so now I just brought up this picture here as a motivation for what comes next. So what comes next will be I'm going to tell you again what the Coulomb branch is associated to those quiver varieties. Okay, so now we start our new topic. Okay? Okay, so I'm going to tell you about something which you may not have seen before. Well, maybe you haven't seen any of this before, but this thing is maybe the least likely, but my favorite topic, affine Grassmannian slices. So I start now with a reductive group. So this group G has nothing to do with the G in the previous section. Actually, it has something to do with the G in the previous section. It's going to be the group whose Dynkin diagram appeared in the previous section. Okay, so this G is like some group, probably not a product of GLs, maybe a single GL, maybe any other group that you like, but some reductive group, which is related to the Dynkin diagram of the previous section. And we're interested in its affine Grassmannian. So what's affine Grassmannian? All right, GR. So I take G, and I look at its points over the ring of power series, I look at its points over the ring of Laurent polynomials in one variable, and I divide by G over the ring of polynomials in one variable. So at first glance, a weird thing to do. This is not a normal subgroup, so this is just like a quotient of a group by a subgroup, so just the cosets. But the way you should think of it is it's like a G mod P. So it's like a usual finite dimensional flag variety, but in an affine setting. So this G over Laurent polynomials is like a loop version of G, or affine version of G. Affine not in the sense of algebraic geometry, but affine in the sense of representation theory. So it's a loop into G, and this is like loops into G divided by arcs into G. Another manifestation of this space in the algebraic geometry language is that this is a moduli space of pairs, P, phi, where P is a principal G bundle on P1, and phi is a trivialization of this principal G bundle away from the point 0. So I take P, restrict to P1 minus 0, and I want this thing to be I've fixed a trivialization, an isomorphism with the trivial. This is the trivial G bundle on P1 minus 0. And the reason for this equality here is the following. If I picture my P1 like so. and I have my bundle trivialized over there, then if I pick a second trivialization of my bundle on the other half of the P1, I can now I have sort of two trivializations on C star. I can compare my two trivializations on C star. Comparing the two trivializations of on C star gives me an element of this group. This group is the same as the group of maps from C star to G. So comparing my trivializations on this C star, I get an element of this group. But to make that comparison, I had to pick the brown thing, which was a trivialization on P1 minus infinity. So then I have to mod out by the choice of that trivialization on P1 minus infinity, which is this subgroup. So that's the reason for this equality, heuristically. Yeah? Yeah. Yeah, these P and this P are totally unrelated, unfortunately. This P0 means the trivial principal G bundle. So just G cross P1 minus 0. In the case when G is GLM, there's a nice way to think of this Affine-Grassmannian. Well, there's two nice ways to think about Affine-Grassmannian. One is to continue as here, but think that P is now a vector bundle, because a principal GLM bundle is the same as a rank M vector bundle. Or you could then take sections of that rank M vector bundle over A1, and it brings you to this description, that the Affine-Grassmannian is the same as a set of all CT lattices inside CTT inverse to the M. So maybe you're familiar with thinking about Z lattices in R2. Those are just free Z submodules of R2 generated by a basis of R2. So usual kind of picture of a lattice. And here it's the same kind of thing. We take a basis of this CTT inverse of the M and consider the CT submodule generated by it. That's what's called the lattice. And it's not hard to see that this Affine-Grassmannian defined this way is the same as the set of such lattices. Okay, any questions? Yeah? No, so yeah, that's a very good question. So quite often, this thing is defined like so. And they're just the same thing. They're just isomorphic, no matter what G is. In this language of the principle, there's two reasons why I did it in the polynomial version today. One reason is because it makes this part here a little more palatable. You have P1 instead of formal disk. So if you do this thing, it's like the same thing, but here you put a disk, formal disk, and here you put a puncture disk. And second reason we'll come to in a second, I really will, not just for some slightly more non-trivial reason, I want to actually have P1 here. But it's the same thing. There's also a slight different variant where you do this, but change this thing a little bit to only have polynomials. That thing you get a slightly bigger thing, which is a scheme rather than an in scheme, called the thick Affine-Grassmannian, but it's also not very different. Any other questions? It's an in projective variety. So it has an increasing filtration by projective varieties. Oh, no, yeah, over spec C, yeah.
The lattices are rank M or
Rank M, yeah. Sorry, by lattice, what I mean is I take a basis of this thing as over this ring, and I take its span over this ring. Okay, so a little bit more of the combinatorics of the Affine-Grassmannian. So as I mentioned right at the beginning, this Affine-Grassmannian is like a flag variety or like a Grassmannian. And maybe you're used to, inside of flag varieties, you have these special points coming from the Weil group. Or in the Grassmannian, you have special points coming from coordinate subspaces. You know, there's in the Grassmannian GKN, there's n choose k coordinate subspaces. So this is the analog. Given a mu, which will be a homomorphism of algebraic groups from C star into T. T is the maximal torus of G. Such a thing is called a coate of G. We get a point called T to the mu in the Grassmannian. What's this thing? Well, this mu is a map from C star into T. T is a subgroup of G, so it's a map from C star into G, which happens to be a map of algebraic groups, but in any case, just a map of varieties. And I already said that this is the set of all maps of algebraic varieties from C star into G. So that's in what sense this thing gives us a point in the Grassmannian. We'll see it more concretely in a second. And then we're going to form the orbit of this through this point of the group that we quotiented by on the right. So now we can take the left orbit of the group we quotiented by on the right. So this is an analog in our flag variety, usual flag variety or Grassmannian setting of forming a Schubert cell. So these are like the coordinate subspaces or those like Weil group, fixed Weil group points in the flag variety, and this is the kind of like a Schubert cell. So this thing is called, what should it called? Kind of something called spherical Schubert cell. That's called. I mean, it would be called variety if I took the closure. That's why I'm calling it cell rather than variety. Okay, let's look at the example. Let's take GLM. So what does one of these coates of GLM look like? Well, it's just supposed to be a map from C star into the maximal torus. So any map from C star into maximal torus just looks like, I just pick some numbers, lambda 1 up to lambda m. I don't know if it says m or not. Lambda 1 up to lambda m. I put those numbers in the diagonal, and I just have like t goes to t to that power. That's a map from C star into GLM. And now I just consider this thing as a matrix. Leave t as like a variable. So now this matrix becomes an element of this group over Laurent polynomials. So that's t to the lambda. So t to the lambda is this matrix, which is an element of this group over Laurent polynomials, but now regarded inside this quotient. So regarded in the Grassmannian. And then, as I said before, we can take such orbits. And this is a natural description of this lattice model. So it's a set of all lattices. Just for simplicity, let me demand that, oh yeah, there was this condition of dominant, which I didn't tell you at all what it meant. Let me not bother telling you what it means, but in the case of GLM, either you already know, if you're familiar with kind of Lie theory, you probably already know what it means, and otherwise it's not going to mean that much. It means this pairing with all the positive roots is positive. Okay, not negative. In any case, for GLM, what it means is that it's a sequence of m integers, and they should all be decreasing. And finally, for simplicity in what follows, I'm just going to ask that the last one be positive too. That's not necessary to being dominant. That's just going to make the answer to what I say next simpler. Then Gur lambda, no bar. Gur lambda is a set of all these lattices that are actually already contained in what's called the standard lattice. So the ct to the m. And moreover, if I take the quotient of c to the m by L, it is isomorphic as a CT module to this thing on the right. Another way of saying it is that on this quotient retains an action of the linear operator T, and T has Jordan blocks of size lambda 1 up to lambda m. Yet another way of saying the same thing is that we could say in terms of this principle of G bundles, okay, let me write it. So it's the same as saying I have a vector bundle, which is actually a not a sub-bundle, but a sub-coherent sheaf of the structure sheaf, direct sum m times. So it's a sub-coherent sheaf of the trivial rank M vector bundle. And the quotient is isomorphic as a coherent sheaf to sort of the analogous thing that I wrote over here. Supported at, first of all, the quotient is supported at 0, and as isomorphic to the coherent sheaf corresponds to that module over there. So some, okay, I won't bother writing it, but you know what, well. Okay, so, sorry, yeah, I slightly changed this here. So I had this mu, which was supposed to be like any co-weight. Then, yeah, so mu is a map from C star into T. So a map from C star into T, it's a map of algebraic groups from C star into T. So in particular, a map of algebraic varieties. And a map from C star into T of algebraic variety is the same as a point of T over Laurent polynomials. Because Laurent polynomials. So it's a point of T over Laurent polynomials. So it's a point of G over Laurent polynomials. So it's an element of this thing here, G over Laurent polynomials. Maybe I'll just write that again. So this thing here is the same as maps of now not maps of groups, just maps of varieties from C star into G, mod maps from C into G. Maybe I should. C here doesn't mean spec C, it means like A1. Okay. And in terms of in the GLM case, it's this matrix. And sorry, I changed notation. Psychologically, for me, mu always means, actually it doesn't, well, mu here, I'm using mu because I think of it as just an arbitrary co-weight, and I switched to writing lambda because now I want it to be dominant. And the only reason why I want it to be dominant is because so you just get one representative. It's just if it's not dominant, any things that are not, any co-weight is related to a dominant one by the action of the Weyl group. And if you change by action of the Weyl group, it won't change this orbit. So it's not that important. Okay. How are we doing on time now? Like 2 minutes. Okay. Okay. Well, I think we can finish the thought here. So now, okay, now if for some strange reason mu is dominant, despite me saying that I was using mu as the not necessarily dominant one, now mu is going to be another dominant co-weight, and I'm going to form this opposite orbit. So I take this opposite group. Opposite group is the following group. So I can look at G over polynomials in T inverse. It's a fine group. And I don't want quite to look at the whole of G over polynomials in T inverse, but what's called its first congruent subgroup. So I consider the kernel of this evaluation map like so. This step is not very important. It's just to make the things actually transverse. So this makes a family of orbits which are transverse to these Gur lambdas. So I didn't tell you this, I don't know, not to scare you, but the affine Grassmann is infinite dimensional. And Gur lambda is nice and finite dimensional. These W mu's, though, are infinite dimensional. They're, in fact, finite codimension. For example, when mu is 0, this W0 thing is open inside of the affine Grassmann. It's almost all of the affine Grassmann. So it's infinite dimensional. And so this makes a family of orbits which are transverse to these Gur lambdas. So these guys are some nice finite dimensional things. You can picture them some kind of spheres. And these guys are some big infinite dimensional things. In this analogy with the finite dimensional flag varieties, these are like kind of opposite Schubert cells. But in the finite dimensional flag variety situation, Schubert cells and opposite Schubert cells behave almost the same. They're both finite dimensional. But here, the Schubert cells and the opposite Schubert cells behave totally differently. Okay? So one family is finite dimensional, the other family is infinite dimensional. These guys are transverse to the Gur lambdas. And we're going to intersect them. So we're going to form W lambda mu, which is made by intersecting those Gur lambdas, or more precisely, their closures. So this closure is actually a finite dimensional projective variety. This guy is an infinite dimensional kind of affine variety. I'm going to take their intersection. It turns out it has the structure of an affine Poisson variety. I guess I'm pretty much out of time. So we'll just, it's probably not enough time to continue, so we'll just resume here next time. But there's a question, yeah?
So this transverse statement is that true for any pair of real numbers, or is it?
Well, sometimes the intersection is empty. I mean, like, so more precisely, the intersection will be non-empty if and only if lambda minus mu is a sum of positive roots. But, well, they're still transverse even if they're empty. Intersection's empty.